I'm going to mute myself before you are overtaken by the sounds of gardening.
All right, that sounds good. So we are now live on YouTube as well, and it looks like our participants are steadily coming in. So I want to welcome everybody. This is our 2021 annual technical forum. In this past, obviously, we've done these as live events, but this year we're not quite to that point just yet. So hopefully we can get back to that at some time this year. But I think it's gonna take a few months before we start transitioning to that. So this year's topic is really drilling towards production. And you'll notice that the focus of a lot of these sessions is going to be that topic, that obviously drilling efficiency, drilling accurately, drilling of high quality are all important. But at the end of the day, the objective really is to get to production. And that's what we have. So we're going to have a 2-day event. We have had to do a little bit of shuffling, though. We had some logistical problems with this afternoon's session on wellbore quality. So we will reschedule that. We're checking into that now, but that will probably be within the next week or so that we'll get that rescheduled. So we have the session here this morning, and then we'll break, and then we'll pick it up again tomorrow morning, and then go from there. These sessions are being offered at no charge. Obviously, we recognize the state that the industry is in. However, if you have enjoyed this and you are in a position to do so, if you go to the website, you'll see in the upper right-hand corner of the homepage, there is a donate button. So you can click on that, make a donation. Obviously, the association has been impacted by the virus just like everybody else, so every little bit helps. So we're trying to make that shift and provide these at little or no cost. But if you are in a position to do a donation, we appreciate that. So today, session 1 is the wellbore positioning, and we've talked about this. In fact, I think John, it was you that had coined the term ROP junkies, and I think we have certainly seen a lot of that. But it is important that the well is actually placed into the appropriate position. So this is the lineup that we have today. John will do a quick introduction, and then we'll go with Ross, Nate, and Adrian. And Adrian, I see we got the E in there instead of the A. I apologize for that. It always seems to go back and forth. No.
Sorry.
And you notice I spotted that, so I know the difference. But I don't know how that popped into place there. But then and then we'll do a quick 10-minute. There's a sponsor highlight there from Applied Physics. Gary Holman will be doing that, and then we have the second part of the session that goes into the impact of these placements, and then a Q&A session to wrap it up. And we should be done a little bit after 12. Tomorrow, the sessions are going to be on remote operations, role of directional drilling, and MWD. And then in the afternoon, it's drilling towards the future. Dave Hutchinson with Spears and Associates will be doing a market, what they're forecasting for the market for 2021. And then we have a panel made up of a number of distinguished people in the industry that will be giving their impressions of where they think things are going to be going, not just from a market standpoint, but also from a technology standpoint. In other words, what technologies are going to be important. So hopefully everybody can tie back in tomorrow and get that. So with that, John, I'm going to turn it over to you. You are live and you've got the con.
Well, thank you. I am just going to try and share my screen. And I am hoping that you can see my, can you see my slide or can you see my speaker notes?
We can see your slide. Yeah.
You see the slide. Okay, good.
Yeah.
Right. So yeah, thanks, Jim, for the introduction and for the opportunity to take part in this event. Looking forward to 6 diverse and interesting presentations coming up in the next couple of hours, and we will be taking 2 sessions of Q&A. It's intended that the first one is for the first 3 panelists and the second Q&A is for the second 3, but put whatever questions you want together. There is a Q&A box on Zoom for people who are on the call. And I think, Jim, there is a way of people watching on YouTube to get questions to you as well that you can relay.
That is correct. I'll be monitoring the questions on YouTube and I'll pass those on to you.
So we'll take them after each set of 3 presentations, but keep them coming and send in as many as you can. Give these guys as much of a grilling as you want to. So I've been kind of consulting for the last 7 or 8 months now on a few different things around strategy and innovation, and also around some issues around directional drilling and measurement. And also I've been filling my spare time with I'm about halfway through my distinguished lecturer tour for SPE. And on that tour, I've been talking about wellbore quality, which is the subject that got deferred from later on today. And also on the impact of tortuosity on things like completions and production. But I pulled a few slides out of that presentation just to kick this off because I thought they were relevant. And the first thing to note is that we've actually been doing directional drilling for quite a long time. These are, I think, some of the world's first onshore to offshore wells. And this was Huntington Beach in California. And I believe this picture was taken in the 1930s. And we've actually been doing directional drilling now for 100 years. Starting off with kicking off hardwood wedges and then those first onshore to offshore wells, all the way through learning how to steer rotary assemblies, and then introduction of motors with bent subs, bent housings, rotary steerable systems, MWD, and then from the beginning of this century, getting into routinely drilling laterals and unconventionals. So when I joined the industry, I was taught that it was impossible to drill above about 70 degrees inclination, theoretically impossible. And here we are today routinely drilling long horizontal wells. And we've got extremely good at sort of taking wells from surface locations to pretty much where we want them to be downhole. But it's very easy to look at this slide and get caught up on the technology and get caught up on the fact that pat ourselves on the back and say, yeah, we're really good at directional drilling. But I think we've got to ask ourselves why we do it. And I think the reason why we do directional drilling is to allow ourselves to exploit and extract resources like oil and gas. That's what the wells are there for, and that's what should be in our mind when we're drilling the wells. And I'm not sure if it was me that coined the phrase ROP junkies or not that Jim mentioned in his preamble, but I've certainly adopted it because it's a great phrase. And I think a lot of the time we kind of forget about why we're drilling the wells. And we worry more about the depth time curve and drilling wells as fast as possible. And we kind of forget about the fact that after we've drilled them, somebody else has got to come along and first of all complete them, which can be difficult if the wellbore quality isn't good, and then produce from them. And well placement and wellbore quality can both significantly detract from our ability to produce if we get that wrong. So I'm going to give the presenters plenty of time. Just before we move into that, just to put into context what's actually important. And these numbers are a few years old now, and you'll also notice that they're based on $50 a barrel. But to drill a typical US onshore well, it's going to cost you, well, the total capex for the well is going to be between $5 and $8 million. And the ultimate recovery from that well is going to be between $25 and $40 million, about 5 times as much. So when you're thinking about drilling the well, and when you're thinking about the economics of the project, is it better to try and shave a few $100,000 off the cost of the capex and drill the well a day or two quicker? Or is it better to actually put it in the right place and increase that lower number, the number on the bottom of the slide, the bigger number, increase the value of the well? And I think the answer is pretty obvious. I think what we should be thinking about is increasing the value and not reducing the cost. So with that, I am going to get off my soapbox, and I'm going to hand over to our first presenter of this session, and let Ross bring us up to speed on what's happening there. So Ross, it's over to you.
Thank you very much, John. You guys can see that screen now. This must be the most used phrase in the industry at the moment.
Yep, you are live.
All good? Excellent. Oh, I've got a split screen. So hopefully you can see the, you don't see my speaker notes, you can see the correct screen, yeah?
We're seeing the speaker notes.
Yeah, you actually have the speaker notes up here.
It seems to be random which way Zoom does that.
And how do we swap this around? How about that? Is that better?
That perfect.
Perfect.
Good. I didn't
I'm
realize
glad this high-tech stuff isn't too much for you, Ross. That's good.
Far too much for me.
Yeah.
So, thank you very much, John. Thanks for inviting me to come and speak. I am currently, I'm very proud to be the chair of the ICSO committee, or the International Steering Committee for Well Survey Accuracy, which is a very long title for an organisation that's got a fair range of breadth to it as well. And I just wanted to quickly go through a kind of introduction of what ICSO stands for and what it kind of means for the industry. But before I do any of that, I think we need to talk about why we bother surveying a well in the first place. So really, fundamentally, we want to avoid hitting other wells whilst we drill in a particular field. And the reasons are fairly obvious. Worst case scenario was a blowout, but even hitting another well and damaging another well is an expensive and difficult thing to do, and you can't do that without wellbore surveying. Geological targets, there is a reason we drill these wells, and that's for production, as John's already said. And you really are going to struggle to get any form of idea about what your reservoir looks like if you don't have wellbore surveying. And wellbore surveying, to be honest, has been around as long as directional drilling has. So the two are very, very closely tied to each other. Reserves estimates for most of my clients, I work for Schlumberger, but most of my clients, the reserves estimates drive the net worth of the company. So you can't do that without wellbore surveying either. Wellbore quality and wellbore surveying are very closely tied to each other. If you surveyed every 500 feet, you would have what appears to be the world's best tortuosity in a well. If you survey every 1 foot, you get the truth. So somewhere in between there is what your actual wellbore quality is. And perhaps more importantly and interestingly is that wellbore surveying is well life cycle data. So from the very start of the planning phase all the way through to the final P&A of that well, wellbore surveying data or survey management is critically important to your well. It's very difficult to do workovers, and this happens quite frequently when you don't have the original survey for that well. Casing and completions, obviously, they are difficult to run casing completions in tortuous wells. It'll also be very difficult to get or cut casing and pull casing out of a well when you're trying to P&A it if you didn't know about the tortuosity of that well. Geosteering, obviously, and drilling targets are wellbore surveying is critically important in order for you to be able to make sure you are where you say you are. But perhaps more interesting from a geosteering perspective, we have some amazing LWD tools that now give you huge levels of detail about the reservoir and how the reservoir looks. Where I think we have a bit of a problem is that this the way the reservoir, the way we take that data, which is in 2D, we actually have to put that into a 3D model, and we have to understand the uncertainties associated with that 3D model and the data you're putting into it in order for you to get a good idea about what the actual reservoir looks like. I apologise. I have people gardening outside my house at the moment, so that's what all the background noise is. Hopefully, I'll raise my voice and you can still hear me. So, what does ICSWE stand for? This is a mission statement. This is kind of the original mission statement, and really it's about producing and maintaining standards relating to wellbore survey accuracy. Coming up with some specific terminology for accuracy specifications, and come up with a standard framework for modeling and validation of tool performance, which was its primary aim actually at the start, and to raise awareness and understanding of wellbore survey accuracy issues across the industry. Basically, until ICSWE was formed, surveying was something of hardly a black art, but there was an awful lot of money poured into surveying, and wells were very, very heavily surveyed, because money was no object. But the problem was that understanding the uncertainties associated with each individual survey tool, be it an MWD tool or a very high accuracy ring laser gyro, for instance, was very difficult for the industry to grasp. So in 1995, ICSWE was started, and the first real bit of work that came out was a kind of industry standard MWD error model. And that was kind of revolutionary at the time. Nobody had ever tried to do this before. There have been error models tried before, but the industry itself hadn't got together to actually produce its own model, if you like. And this was like the minimum standard expected of an MWD tool for this MWD model. Then in 2003, the SPE asked if we'd like to join the SPE and become a technical section. So we became the SPE Wellbore Positioning Technical Section, which is even just as much of a mouthful as ICSWE is. But that has broadened the horizon somewhat and allowed us to meet with other technical sections and improve our educational part of what we do. But fundamentally, if I'm to bring all of this together, ICSWE is a group of very passionate volunteers who give up an awful lot of their time in order for us to produce kind of de facto standards for the industry, error models, etc., in a kind of ever-evolving frame, if you like. So whilst it originally started off, ICSWE started off just looking at error models, this has actually expanded into anti-collision, expanded into survey management, expanded into, to some extent, into QA/QC, etc., for survey tools. So it kind of, the whole thing is broadened out very significantly. And I think, well, we're going to show that in the next slide, but basically what we actually do is, and the really big part of this is educational, is our output. So we have two ebooks, one on ranging well intercepts and one on survey, wellbore surveying in general. And we've had over 60,000 downloads of them, and I'll give you a link at the end that anybody can use to go and download those books. But they've been very popular and very useful. We've produced error models and frameworks. That was kind of the first thing that we really got involved in, and that has grown arms and legs. Started off with an MWD model, then started off with gyro models, and now there's what's called the OWSG, or the Operators Well Survey Group, that produced a whole bunch of error models with all the terms inside them for use for anybody to use, any company to use as a standard or a set of error models. We produce a lot of SP papers, but recently we produced some SP papers on survey management and anti-collision guidance. In other words, both. So it's how you look, what you need to look for from an anti-collision perspective, and some new ideas, or shall we say, a unified idea about how you would go about measuring your likelihood of collision. So a set of rules and a set of standards, if you like, about how you look after survey data and how you use survey data. And these have sort of become de facto standards. And the reason I say that is ICSWA is not a standards body. And the other thing I think I need to point out right now is ICSWA also doesn't, and this is a question that comes up quite frequently, ICSWA does not qualify error models or qualify survey tools. That is up to individual companies to do that themselves while satisfying the framework in which those error models have to fall. But in terms of de facto standards, from a survey management and AC guidance, these SPE papers, if you like, if we have another, and I really hope this never happens, but we have another incident with where we need to drill a relief well, we have a blowout caused by a well collision. In that case, regulatory bodies get involved. This industry published, these industry published papers, and the fact that ICSWA exists and is part of the SPE will by default end up being a standard by which people will be judged. So we're not a standards body, but I think ourselves, like other technical sections inside the SPE, do actually produce de facto standards, if you like. We have biannual meetings where we discuss new technology and new techniques, surveying techniques. And we have the subcommittees, they meet, and that's where all the work gets done, really. And it's a great opportunity for networking. I'd really love to encourage any of you on the call, if you want to come to the next meeting, which will actually be online. That will be plastered all over LinkedIn, and if you happen to be part of the email blast that we send out for ICSWA, then you'll be able to see that as well. I need to talk very briefly about each one of these work groups. The first one came along in 1995, the error model group. Then it was decided, once the error models were established, the MWD error models were established, that perhaps anti-collision or collision avoidance needed to be thought about as well. And in 2003, that was developed, and that was more, it started off just looking at terminology around anti-collision and understanding how different companies were doing anti-collision. Then it really, under the stewardship of Steve Savern, has really turned out into a set of guidance for the industry on how you might want to do well avoidance or anti-collision. The education subcommittee and the well intercept subcommittee appeared in 2011. Education, because we had so much information to give to the rest of the industry, that we needed somebody to look after how we were going to go about doing that. And they've generated a lot of ideas. That's where the ebooks came from. And the well intercept, and actually the website for that matter, the well intercept committee arrived because first, we like to avoid wells for the most part. Sometimes we need to hit them. So we, the well intercept committee appeared and has had various chairmen, and it's still around. There's a lot of work, and that's actually where a lot of the work for the ebooks from a ranging perspective came from. But up to that point, I think ranging and the understanding of well intercept was not particularly well understood. And I think this ebook is a great guide to demystifying some of the terminology, at least, and some of the technology. Then in terms of more recently, we had a QA/QC subcommittee group, which was looking at, it's all very well taking surveys down the hole, but how do we establish how good those surveys are? So we're looking at perhaps standardization of survey QA/QC and how we pass data between each other. And the OWSG is the Operators at Well Survey Group. It got together to develop a set of, well, two things happened out of this actually. One is to develop a set of standard error models that anybody could use, which they published, I think, in 2017. And the other one that came out of this was that there's, with the API, we've been working very closely on what's called RP78, which is all about, basically well positioning and anti-collision, etc. And this will become a standard going forward for the industry. And there's been a huge amount of work between OWSG, the education group, in fact, the whole committee, to be honest, trying to develop best practice for this API, which will hopefully be coming out for review this year and will be published after the review. I don't quite know when that might happen. But that's really what we do, mostly education, but these work groups are the ones who are producing all of the work. And I have to say a huge thanks to all of those who do that, because ICSWA would be a bit irrelevant without you. The final thing is, in terms of resources, we have ixwa.net, which is our website, and then ixwa.net ebooks. So there's 2 sets of ebooks, one on, as I said, the theory behind wellbore positioning, and the second one on the theory and the practice behind well interception, ranging, etc. If you go to the website, there we have lots of information. We have all the past meetings there. We have all of everything we've ever published, and you can go in there, and you can, in the ebook, for instance, you could go and you can see everything from eigenvectors to you know, what IXWA stands for. So we've got a huge range of material for anybody to go and look at, and that's what we're going to continue to do. I think IXWA continues to evolve, and we want to be closely involved with the wellbore quality side of things as well, and that I think will be another subcommittee, and we're very happy to work with IDD and others on getting the message out about wellbore quality and stop us becoming ROP junkies. And with that, I'd like to say thank you very much. I believe I might have gone a little bit over 10 minutes, and hopefully you could hear me whilst the grass was being cut outside. Thank you.
Yeah. No, you're in good shape there.
That's good. Thanks, Ross, for that. And just before we move on to Nate, Robert Wiley put up a note to let listeners know that IXWA will soon be offering the certificate course on wellbore surveying. So watch the website for those details. So thanks for that. And Nate, if you're ready, if you want to assume control, we'll hand it back on to you.
Can you see my screen?
I can, yeah. It looks good.
Great. Well, I wanted to start off and kind of thank everyone as well. Thank the IADD. John, thanks for the introduction and the invitation to come present. Also got to take a look at the attendees that we can see on Zoom. A lot of familiar faces. Wish I could see everyone, but hopefully COVID is coming to a close. So we'll get together soon. My name is Nate Anderson. Gemini is what I'm going to talk about today. Gemini is a product, but it's also kind of the story of a different approach to finding a better wellbore placement solution. I've personally been in the industry for 14 years now. I work for Neuralis, and Neuralis is an MWD technology company. So I want to talk a little bit about our approach and our journey through the current market. So when you give the challenge to an engineering group of better wellbore placement, we start to think about building just the perfect tool, right? So the self-operating napkin, that's kind of where we get going at. We say, we're going to engineer this. Tool is going to be perfect. It might cost a lot of money to get there, but this is what the oil company said they wanted. We know if we build this perfect contraption, we know they're going to come and buy a bunch of tools, and everyone's going to just be doing great. So we get stuck. We get stuck in this tunnel vision of the perfect tool. And then something like 2020 comes around, and it kind of resets what you were thinking was the goal. And I'll be honest, this has really been happening since 2015. So from 2015 to 2020, everybody's budget gets reset, and we kind of started the journey of the perfect tool. And you have to take a step back. You have to say, hold on a second. Let's go back to the original problem. The original problem is wellbore placement, right? Where are the errors associated with that? Based upon the last 5 years, we now have new constraints. Oil companies, and this is my opinion, are no longer accepting paying more money for drilling wells. We know they want better wellbore placement. They want it for cheaper, and they want to drill it faster. Seems like these three things are kind of at odds with each other, but that is really where the market is. If you're out there building a tool that is 4 times the cost of somebody else's tool, and it doesn't give you at least 4 times the benefit, I would question if that's going to be successful in today's market. There's just not as many rigs drilling, and 2020 has reset everything. So the thing that changed our approach is we went back to the original error model. We said, okay, from the MWD standard error models, a random well, fairly long lateral, you get 164-foot ellipse of uncertainty on the semi-major axis. If you take everything you can do with magnetic surveying, corrections, IFR2, SAG, multi-station analysis, you get a 46% reduction. That's significant. That's why oil companies are willing to pay these third-party survey QC companies, because they're getting almost a 50% improvement on where their well is being placed. We took a look and said, well, let's build a tool based upon the standard, or based upon that maximum error model, that has twice as good on the accelerometers. Let's look at 4 times as good on the accelerometer accuracy. What is our result? And the result was kind of disappointing, 10%. 10% is the EOU reduction from the best you can do in magnetic error modeling. And so it really comes back to, you know, what is going on here that we can only get a 10% improvement by making a product that is 4 times as accurate as the standard error model that we're used to. We know that traditional surveying methods struggle to capture trajectory changes between static survey points. I've been in the industry for 14 years, and I have listened to Ed Stockhausen talk about this effect for probably 13 and a half of them. We do not know, we do not quantify very well what happens between survey station intervals. And we use minimum curvature, it's a smooth curve. We know things that we can't describe happen between those survey points. So lack of survey density is important. We also have the constraint that oil companies are not going to allow us to continue to survey more often. So we want more surveys, but we can't do it because of costs. So building that tool with 4 times the accuracy, it can help. But correcting for misalignment terms and survey frequency and understanding what happens between survey points can help a lot more. That is the solution without costing rig time that we took away as a lesson from the market reset. So this is kind of a generic slide. I'm talking about our company, but it applies to everybody. The thing to do is to really identify what is your core competency. And for Neuralis, we have a core competency of magnetic surveying instruments. We have a core competency of transmitting and detecting data. And we do a pretty decent job of moving that data around through the cloud to various mechanisms. That's what we do well. What we don't do very well is gyroscopes. And when I think about the gold standard for downhole surveying instrumentation, I think gyroscopic surveys, right? That's one of the best things you can do to get a very accurate survey. We're also not very competent at well modeling. So we do a good job of transmitting that data, but we don't really get involved in the modeling. So 2020 is reset budgets. We've identified what we do well. We don't really think there's a market for us to try to go build this super duper tool. What about some synergies? And so Gemini is a story of identifying synergies in the industry and leveraging those synergies to get a pretty good result. So what is Gemini? You know, at its most purest form, Gemini is a pretty basic concept. It's something that's been done before, certainly. It's 2 downhole instruments in the same MWD tool string with a distance between them that is transmitting survey data. That is Gemini. You know, we've seen this in the past. We have rotary steerables that have survey information in them. We have MWD tools that have survey information in them. Not a great leap, but something we're very good at, downhole hardware. Getting additional data uphole, another core competency of ours, and then being able to, what can we do with that data is really the next step. That's where Hi-Fi Nav comes into play. So Hi-Fi Nav is a superior QC product, and it's a statistical synthesis of multiple survey points combined with steering and sliding consideration of better defined wellbore path. Hi-Fi Nav fills in those pieces where we're lacking core competency. We're able to describe the wellbore better between survey points, and Gemini gives us additional survey information. So how it really works here, customer rigs up Gemini, runs it in hole, transmits that data to surface. Rig time impact is always a concern. We're sending more data. But the way we currently drill wells today, that customer is already drilling ahead. They've already tagged bottom. They're making hole while the survey is coming up. That's a unique thing. It allows us to get a little bit more data at the survey point, data that can tremendously help the statistical synthesis of additional surveys and Hi-Fi Nav algorithms. Once we get the data, it's transmitted over the API to the cloud. Hi-Fi Nav does its corrections and adds all the magnetic correction pieces. Also adds multiple survey trajectory points. So we take that minimum curvature of 90 foot or 30 foot or 200 foot survey frequency. We add waypoints in between there. It's then sent back directly over the API, and then it sits in the MWD system. From that point, systems that are sitting on top of the MWD system, like the EDR or other tertiary systems. They're fed the additional survey information. And the result is that we can drill ahead in real time with the most accurate survey listing available to us. So this last piece is, how accurate are we talking about? This is a result from a couple pads we drilled here recently, drilled by our sister company, Gordon Technologies, running Gemini, running these products. About a 2-mile lateral. One of the pads was drilled south, the other 15 degrees off south, the other pad was drilled north. The blue circle is your MWD standard error model. The yellow circle is your MWD error model with IFR and MSA. And the orange circle is using that data, leveraging core competencies, not building this completely different hardware product and getting between 20 to 30% ellipse of reduction uncertainty. So that's kind of the end of what I want to talk about. I know it got a little commercially in there. It's not intent to sell. It's just talking about our journey, how we kind of took a step back and said, well, we know what we would love to do as engineers, but this is what the market is telling us we should do to continue to survive and hopefully improve the journey of wellbore placement.
Hey, thanks, Nate, for that. Enjoyed that. And I did say we'd take questions at the end. There was a specific question came in. I don't know if you can see it in your Q&A box, but from Paul, why are you using IFR2 in your tool error model?
Oh, I'm sorry.
Because it's specific, then we might as well take it now.
It was just the error model I had. I mean, IFR2 is an improvement over IFR1. Yes, I'm not as technical as an expert on this. I apologize, just presenting the results. But if that's a mistake, that was the error model I was told to use it as it provided for the yellow circles.
Right. Okay. I'm sure if there's any more clarification needed, then Paul will come back. But yeah, thanks for that. We will now move on to Adrian, who will talk to us. I think Adrian's going to talk to us about sort of GWD. So Nate, if you can stop sharing, then hopefully Adrian can start and we can move on.
How do I do that?
Green button at the bottom of the screen.
Thank you.
And then you probably have to pick a window or an application.
And okay. Are you seeing the notes or the?
I don't.
Seeing the right.
Neither.
Not yet.
No.
No, just seeing you still.
Okay. It says here was. Sorry.
We're going to miss all this one day, aren't we?
Yeah. You can see the screen now.
Yes, perfect.
Okay. All right. Sorry about that. Just use a lot of Teams, but not Zoom too much. So very good presentation by Nate, and a few things that, well, they kind of draw a parallel and then a distinction. I work for Gyro Data. So what we do is, well, Gyro, so that's our expertise. We actually, try to get into other markets, but then decided to go back to our core business, which is running gyros. Because this is what we do best. This is what we've been doing for 40 years now. So we are working on that. And we are, also the other distinction, I guess, is that, we are working, or we've been working on the hardware aspect and try to make a better tool, a more accurate tool. So for you, all of you that don't know, a GWD or gyro-while-drilling tool is a tool that uses a gyro and connects to an NWD in the BHA. And basically what we do is we, at each connection, when the tool is not moving, we take a survey. The difference with an NWD, of course, is that we use the earth rotation to compute the azimuth, which we call the gyro compassing. The way that we do this, and other companies do the same, we compute the azimuth and the QC parameters downhole, and then send that information to the surface. And we do this for, I guess, a couple of reasons, but one of them is that usually there is no correction associated with the gyro, and I'm going to talk a bit more about that later. But there is not really an important advantage of sending all the 6-axis data. The other thing here is that, well, if you start with the surface, you can use a 2-axis system, which was the start of what we have. And then as you get to a higher inclination, you need to have a 3rd axis to compute the data. The other thing that a gyro-while-drilling tool allows you to do is to compute what we call a gyro tool phase, which is basically a reference when you are vertical and you have magnetic interference. So instead of using the information from the magnetometers, you can use a gyro, integrate that signal, and you can steer the well in the vertical or near vertical. The first GWD tools came about in the early 2000s, and they were spinning mass. But well, there are at least now 2 companies with a GWD tool using solid state technology, because all the advantages that they come up with, that they result from using this technology. A bit of a comparison, just so we have a better understanding why will you use a gyro. Most of the wells, or all the wells actually, are drilled with an NWD tool, and only a few of them use a gyro. So just to go through why will you consider running a gyro? So magnetic sensors are very good sensors, are very stable and rugged. From an instrumentation point of view, it's almost a perfect sensor. The bias, stability, the scale factor, misalignment, it doesn't change too much. It's easy to model. You can calibrate them and trust the measurement. The other aspect is that they are really not affected by any movement. So that means that you can take a survey in a very short time, and you are good to go. The problem with these tools is related to not the actual tool or the sensor, I guess, is the reference that you use to determine the orientation. The magnetic field, the Earth magnetic field, is not a stable reference. It changes over time. It's a slow movement, but you have to keep track of that. And there are also diurnal variations. You have, in addition to that, local anomalies, which are not very easy to model, but it's possible to compensate for that. And then, depending on your latitude, you will have different effects of magnetic storms or solar winds. In addition to that, in addition to the reference, you have all the magnetic material, or the possibility of the material near the sensors to get magnetized and affect the measurement. So you have still from the BHA, from the motor, from the bit, you have nearby wells that will corrupt the measurement. You may have some ore deposit that affect the measurements and magnetize mud. And there are probably some other ones. There are several techniques to improve this and to make correction, but depending on the well profile, the geometry that you have, and how many of these affect at present at the same time, it's really hard to do these corrections in a very reliable way and also be able to QC it. The gyro on the other side, especially the solid state sensors, I think, yeah, I'll refer to those from now on. They are somewhat new. We have introduced the first one in 2018. So they are more rugged and stable than the spinning mass, but still, I think I cannot say they are as good as the magnetometer on that sense, because we don't have the whole history yet. But the biggest problems with the gyro is that they are greatly affected by movement. So movement, we refer usually to displacements and rotation. So any rotation that the gyro will see, well, cannot distinguish that from the Earth rotation that we want to measure. But if we can deal with that, that's it. Really, the Earth rate that we measure is a stable reference. It doesn't change over time. So if we have any issue with the survey from a gyro, is the gyro. You don't have to worry about the modeling. You don't have to worry about interference or any other thing. And another advantage that has is that it's not affected by magnetic material. So this, well, results in benefit, as I said at the beginning, that we can drill now wells in proximity with other wells, and magnetic interference is not a problem. And we have made the study here that in many unconventional wells from a pad, we end up drilling a notch to avoid the magnetic interference from the other wells. Well, if we were to just drill a well and ignore that effect, you may end up with a well with a better placement and reduced tortuosity and reduced torque and drag at the end of the well. So this is an example of an advantage. We can place the sensor pretty much anywhere in the PHA and very close to the bit to allow well, drilling a better well and to have closer information to what's going on. This has been used as well a lot for detection or error detection when compared to the NWD. So the beauty of this is that now you have two independent systems based on two completely different principles. So as John mentioned at the beginning, if you place a well in the right place and you well now avoid having an error, an undetected error, you're going to pay off with the better production and reservoir mapping. And the other advantage is that usually there is no correction to the data in real time. So the typical application for this when we started with the GWD was a top hole section, usually near vertical for a platform or semi-submersible. And then we start getting as well into land congested fields. We use this for sidetracks. And lately, because of the solid state technology, we are using this tool for reduction of uncertainty for infield drilling. We were recently in a project in Canada in which, well, it was a mature field. They wanted to drill more wells. And even with the multi-station analysis, error reduction, they thought they can only place 5 wells in that field. And when they look at the uncertainty that we would have running from the surface to the bottom with the GWD tool, they were able to place 10 wells there. And that's what we did. And well, hopefully we'll write a paper about that to get more details. And the other thing that we are doing now is, or that the operator is appreciating, is reduction of the uncertainty in the reservoir section. This is just an example similar to what Nate showing there, I guess, that any survey tool will produce a number. After all, an azimuth value is just a number between 0 and 360. So any survey tool is able to do that even if you have a large error. The key aspect of this is the uncertainty and being able to judge the accuracy of the survey. Many times we were asked, well, what's the azimuth uncertainty of this tool and how this tool compared to an NWD? And it's not a question that can be easily answered because there is no one answer to the question. Basically, in order to establish that, we need to create an error model. We need to know the uncertainty of the tool, the uncertainty of the different error terms like bias and scale factor, and then translate those into azimuth and then into a positional uncertainty. So just to give you an idea here, this is a test well profile. It's called the ISQA well number 1. So it's a North Sea well at 60 degrees latitude and has well, start vertical, has a long tangent section, I believe at 60 degrees inclination, and then you end up at horizontal with 75 degree azimuth, 8,000 meter well. So very complicated well for a survey tool. And if you run an error model, similar to what Nate have there, we see the error uncertainty of the NWD using IFR2, SAC, and multi-station is this red ellipse, and the Quest GWD, which is our solid state GWD, without any correction. And this is the uncertainty that that we have for this tool. Something that sometimes I struggle with our marketing team is, well, sometimes the uncertainty of the NWD and the gyro are very similar, or sometimes it's the other way around. Well, yeah, that's the way it is. There is no linkage between the two, and it's really wellbore dependent. And if you really need to know or want to know, someone asked me, well, what would be the uncertainty of a well in Colorado? Well, I had to run the error model, and it's not the same whether you are north or south or east or west. I think I'll leave it there. And just to close with some remarks, and maybe this is also a bit of a commercial, but with the solid state gyros, at least for us, these are things that you may say that the NWD has been able to do for many years. But as I said, for us, it's a breakthrough that we finally have been able to complete these things. In 2018, we complete the first well from surface to TD, several runs with the same tool, 20,000 feet. And since then, we have completed many wells like that as well. Before, the GWD tool was only used for areas of magnetic interference, and then it would be switched off, and you continue drilling your well with the NWD. We are also running this tool in the reservoir section in the North Sea, and we are getting very good feedback from the operators, because this is something that they wanted to do, and the previous technology with the spinning mass, they didn't survive this environment. And it's the same now. We've been doing some initial jobs with air drilling, and this is something again that for a spinning mass gyro, we will never survive. We'll never even attempted to survive that. And now we are running these tools for this air drilling application for, in this case, is the vertical section. But again, it allows us to run in this environment. And the final thing is that, well, in this time with COVID and the idea of reducing the number of people, we are able to achieve that now with this tool with a lower power consumption. We can put the tool in the collar and ship it to the rig and run it without personnel on board. That's all I got.
Okay, thank you, Adrian. And thanks to all three of our sort of presenters for the first part. So we've got a scheduled break in 13 minutes. So we've got a little bit of time for questions. There is a couple that have come in, and they're kind of specific. I'll throw those out first and then maybe move into some more general questions. There was a question from Knut about how much time it takes to acquire surveys with GWD. Does it take longer than with a conventional MWD tool, or not? And if so, by how much?
Yeah, well, we can adjust the time. Usually what we look at is into how they're gonna run the tool. So the connection time is 2 minutes or 2 minutes and a half. We will take a survey in a minute and a half and have enough time.
Okay.
If they are planning to take surveys outside the connection, we can adjust the time. It's just that there is more chance of the noise affecting the data. You may pass a QC or not, but so far it has been invisible to the operations because it's part of the connection time.
Okay, that's good. That's good to hear. And there was a question from Michael for Nate, I guess, about Gemini, and that is are you only taking additional static surveys on connections, or is there a any kind of real-time data stream? And do you have memory that allows you to collect data when tripping out? So Nate, you can read that as well as I can.
Yeah. So I want to break that into like a couple of different pieces. Most MWD tools have some sort of real-time telemetry, right? Real-time inc, real-time as. Hi-Fi Nav, that this product that analyzes the data, it's kind of independent, right? But so when we synergize these things, we are taking into account sliding and drilling rotation. We are taking into account real-time information from the MWD. What the Gemini does is kind of confirms what we've been modeling because it's a certain distance back. So it's kind of a redundancy part of an instrument, right? We got a little bit of redundancy downhole, but it's really confirmation that our Wellbore did X between what we thought it did between these 2 points. It also has application to project forward. So we're continuing on this path, but that's kind of what, Gemini is really just additional static measurements, but there is also a lot of real-time data stream taken into consideration, which can shrink the ellipse, right? We want to know what's happening between the surveys. Shrinking the ellipse takes that.
Okay, that's good. From Gregory, question, I guess this one's back to GWD. Is there any continuous ink or as available with GWD, Adrian? Yeah,
we have a continuous inclination, and we have a few ideas, a project of how to get the continuous azimuth, but not today. Only while sliding, but not while rotating.
Okay. What kind of accuracy do you get for the continuous inclination? Can you say?
Well, it's a bit depends on the level of shock and vibration. So on this, we don't have I don't have a good number to. I'm sure we are not as close as good as the Gemini that they are taking all these into account and having two systems, but it's I think it still is being useful for the directional drilling.
Okay, and I guess it's just a question I've got, and I guess any of the panelists can comment on this. But there was a couple of times Nate mentioned Ed Stockhausen, and I'm sure we've all seen Ed Stockhausen's paper on the Stockhausen effect, and how you can get good information from continuous inclination that will give you a better idea of where the well is than just by taking the static survey points and interpolating between them. And do you think that there are improvements in survey accuracy that we can get by integrating continuous measurements? And if so, do you think the bigger challenge a technical challenge, or is it like a regulatory challenge in terms of sort of getting people to believe that the well is where you say it is? If that makes sense.
I'll try to answer that. John, we're doing that right now. So part of our ability to move around data is we can move around real-time data just as easy as survey data on an email, right? The big shift has been keeping everybody's surveys listings up to date, right? And we kind of get stuck on these 90-foot surveys because that's what people are used to seeing. I used to work at Gyro-Data with Adrian, and they had a continuous gyro product that could survey a well every foot, but nobody wants to see a survey 20,000 rows of data. So,
or even when they see it and we give it to them, they say, well, I'm gonna put it here, but I'm not sure what to do with it on the database and how to keep it for future use. So that was a complication that even though we have that, they say, well, give me just a point every 100 feet.
Yeah, so for real-time inc, it is dependent on shock and vibe, of course, but there's enough data out there to validate what your real-time inc results are saying. There's enough survey information to understand if your real-time inclination is trending correctly or incorrectly, even in a given wellbore. We're measuring shock and vibration. So I feel like it's pretty quantifiable. Azimuth a little bit tougher, but the real-time inclination, in my opinion, it can be used. I don't know if there's a regulatory is not really a huge concern. It's the survey to the best of your ability, right? So it's really what is real downhole. And if you run enough confirmation instruments and enough, drilling instruments in the wellbore, that confirms what you're saying. I think we can get there. The technical challenge is handling the data, and so that's what we're trying to work on.
Do you think we can ever?
This,
sorry, Adrian, go on.
sorry. No, I was saying, it doesn't seem to be a technical challenge, but more of a process and just getting it done. I think technically we can do it. There is enough space, and it's not, even though it would be 20,000 lines of data, that's not a huge file.
So, John, if I can just add to the add to the amount of data, what you can do is up front before you've even spoken to the client, work out what it is that they want. You know, are they interested in a survey that defines a well every, say, 1 foot in TVD, and you define everything by 1 foot in TVD, and you don't give them any other information except what defines that change in 1 foot in TVD, and you can approach that challenge in that way. But I think the azimuth side of the business is that's quite exciting as well. I think there's a lot goes on from an azimuth perspective that we don't see because the continuous azimuth is just on the single axis continuous azimuth on tools is not, certainly going east-west is not reliable enough. Sorry, north-south is not reliable enough because it moves around too much. But going east-west, you could actually get some idea. I think we could do better with the information we already have, integrating that into even rotor serial control systems. You know, that there's a lot there, an awful lot there that just sits on the table, gets unused.
Do you think we could ever get to the point where we don't have to stop to survey, or is that like just rocket science or science fiction, I guess?
I would love to see that I'll send you a link to our TrueLink video, but no, that's all commercial. But yes, there already is a tool that's available, but it's not, it ain't cheap. So but it's there and it works.
I think you also need to define stopping. I mean, we're making a hook every 90 foot, but oil companies now in the US aren't stopping. I mean, they're turning the pumps on and they're going to bottom, and the survey is transmitting a couple feet later. So they're I mean, EM systems obviously do it off time, but even if with mud pulse, if you're comfortable with missing your first couple of feet of gamma, which they typically are because they know the formation they're in, they're really not stopping. So that's been a big something we've been able to leverage because of that.
Okay. And we've got a question coming from Gregory Devonish, basically making a point: in order to improve TVD accuracy, we need to measure depth more accurately and not use roughnecks and tape. I mean, I don't know who wants to comment on that.
True.
This is very true, and it's been a discussion and argument for a very long time. There are solutions available to measure the drill pipe every single stand before it goes down hole, but that's only half the problem. The other part of the problem is that when you get below the rotary table, you have temperature and stress on the pipe, which changes the length anyway. So you have to solve both sides of it. It's not just measuring the drill pipe. That'll be a nice start. We also have to start, and it's something we totally ignore and we're perfectly capable of fixing, solve the dynamic part of it as well.
Okay, I think we've got another 2 or 3 minutes scheduled before the break. If there's any more questions from the audience to come in, or if any of the three of you wants to make any other points, or even if any of the other three presenters wants to ask these guys anything, but don't ask anything too difficult because I'm sure they'll get you back in an hour's time. Or if not, we can just take an extra couple of minutes of break, and we can return at what time to return? 20 minutes past the hour, so in 13 minutes time. Oh,
actually, John, Gary is going to do a quick presentation. Gary Holman with APS. We've moved the this in since we don't have the afternoon session, so this will be a sponsor break. And Gary, you can go ahead and share your screen, and we can go on. And I see there's a couple more questions that have popped up.
Yeah, there is a question from Knut about how well does your end user understand this issue? I think that's, I'm not sure which of the issues we were just talking about that was.
Maybe TVD accuracy would be my guess.
Maybe, yeah. All issues, it says.
There goes your 2 to 3 minutes, John.
Yeah, there we go. Who wants to take that?
All those issues are, yeah, I mean, that's the whole point of ICSO, I think, is to try and help people be educated and understand all of these issues. And if people won't read SP papers and people won't or don't have the time to read SP papers, and people, you don't need to come to the expert meeting to see what's on expert, but go to the website and have a look at what's there. There's a huge amount of information and enough that people get a very good grounding in wellbore surveying and what goes on. But I think possibly the problem is that I think, John, your presentation, your distinguished lecture presentation touches on all of this, on this concept that you have to understand that wellbore position is key to you understanding what's going on downhole from a wellbore quality point of view, from a well placement point of view. And we just have to keep pushing that message. I don't think there's anything else we can do. We just keep carrying on what we're doing, maybe get a bit more clever with some of our messaging, but I don't think there's much else we can do.
Yeah, I think that's dead right. I mean, from my perspective, and the message I try and get across during the presentation is that I kind of despair sometimes at the apparent, and I don't think it's a lack of understanding. I think it's more of a lack of connection, and maybe the way that we incentivize people, and maybe the way that we manage some parts of the operation. I don't think people are willfully ignoring the benefits of wellbore quality and wellbore placement or drilling bad wells. I think they're just maybe being asked to do different things that conflict.
Yeah,
that can conflict.
I think that goes back to the famous Jack Nicholson line as well. The truth, you can't handle the truth. I don't know if people really want to know what the shape of the wellbores actually is when they get right down to it. So that's why I think 90-foot surveys are so popular.
Yeah, as said, it's very, very easy to make your wellbore look fantastic if you start selecting the surveys you present.
Yeah, right up.
I have been told by one of the operators in the US that they never run a gyro survey on the outermost well on the lease.
We have run gyros, and then when there is a discrepancy, it's like, don't call it.
Sometimes you don't want to know.
Yeah. Yes.
You get paid double to lose that survey, right, Adrian?
Yeah. Yes, something like that. Yes. Don't file it. It's just
Yes.
Okay, so I think we can now move into the sponsor presentation during the break. So thanks, guys. And stick around just in case there's any questions for you in an hour's time.
Well, and there will be afterwards. So Gary, go ahead, share your screen, and let's see what you've got here today.
Thanks.
Right. Well, good morning. Hopefully you guys can hear me properly on the presentation here. So
you're good. Screen is up.
Awesome. Thank you. Well, we're going to talk about our next generation EM transmitter in the technology forum today. And this is something that we've been working on and rolling out here in 2021. So we're hopefully to see some big changes for our systems going forward. Page down. About the company, we've been around a long time. Head office is in Mountain View, California, but we have offices in Calgary and Houston, and we have equipment all over the world in North America. And we design, manufacture MWD equipment, oil and gas sensors, magnetometers, accelerometers, and you can find our website. So we've been building EM transmitters for 20 years, and we have almost a few hundred EM systems in North America and the world. And we're one of the more often used 3P type of EM systems. So people are well used to using our equipment, and they're very familiar with it. But with all the changes in drilling practices, fluids, rigs, faster drilling, formations that we're drilling in, we went back 2 years ago and started to redesign our EM transmitter for the new market that we see. We only had one requirement, and that it had to be a drop-in replacement for our existing AP transmitter. So what we want to do is, if you have one of our existing systems, you can upgrade to our new G3 EM transmitter by popping out 8 screws, 2 connectors, and you're in business. We want people to be able to use their existing equipment and upgrade to the latest and greatest technology to improve their wellbore drilling. So we have a bunch of new features for our what we call G3 or Generation 3 EM transmitter. We have improved power generation. We can generate truly up to 80 watts of power in many different resistive formations. A lot of older EM systems can generate, 20, 40 watts of power in like premium resistance, really specific zones of resistancy. But our new transmitter has been designed so it'll work from half an ohm up to 1,000 ohms of resistance and still drive the appropriate power that you want. I may not advocate 80 watts of power unless I was trying to be a battery manufacturer, but it does give you the opportunity in a Hail Mary situation, the last 100 feet of the well or some difficult drilling area, that you could jump up the power, get through it, and then go back to a lower power setting. This is just a nice little feature we added on for free. We have improved our baud rate and increased our transmission frequency so that we can now transmit up little over 40 baud of data if we had to, and depending on depth, formation, et cetera, but the key aspects of this is that everyone is asking for more data faster, and they want it to be reliable. So we've pushed the envelope. We've pressed our encoding and decoding to improve how we transmit and receive our various EM transmissions. A part of this is that we've added a spread spectrum technology that allows us to transmit across multiple frequencies and channels for your data sets. You could theoretically transmit your surveys on one frequency, your gamma on another, and perhaps tool faces on a third frequency if you so wish to. You can do spread up your data any way you wish, and you can pick it up and decode it at surface, and it comes up seamlessly, like you don't even notice this, but the downhole technology enables you to do so. And the real nice thing about our 3M transmitter that we're talking about when I mentioned the 80 watts of power is that we're trying to do this adaptive formation transmit technology. We've noticed that back in the day, people would drive their EM in like 10 ohms formations, 20 ohms, and almost anyone can make an EM transmitter and work in that environment. What really gets challenging is when people start doing brine muds or salt formations or clays or some of the coal seams, and you can go from like a half ohm to 2,000 ohms resistance, and people expect EM to work, and that's the big knock against EM. EM doesn't work everywhere. It doesn't work in formations. That's why we have dual telemetry. When the EM drops out, you go to mud pulse. This adaptive formation transmit technology allows us to transmit in really low resistance, like half ohm, all the way up to 1,000, 2,000 ohms. We have a customer in China who is trying to do methane drilling out of a coal seam, and they're at 1,500 ohms resistance. And this is a technology they're looking to break open this environment for them. So using the greater baud rates and using more of the EM frequency to transmit, we get greater noise rejection. Not only are we allowed to transmit data across the multiple frequencies, but we're also embedding our synchronization across multiple frequencies. So as everyone knows, as you're drilling, sometimes we get noise spikes on someone turns on the AC unit or they turn the turntable on or something, and suddenly our EM disappears. And if that happens during a synchronization or some other event, your data can go away for a short period of time. Well, the idea of this is that we can spread the synchronization and the data across multiple frequencies. And if we get a noise spike at one frequency, it doesn't affect how we synchronize and recover that data because the other frequencies enable us to stay in sync and matched to the transmission encoding that we've enabled. So we're more immune to noise effects and formation degradation. So you can transmit at higher frequencies at formations you may not be able to in previous applications. Our EM transmission is adaptively adjusted to match to the induction and resistance of the environment. This is what we're adaptive transmit technology that we're now effective at transmitting full power. If you select 40 watts, it'll transmit 40 watts at a half ohm or 40 watts at 200 ohms. It doesn't matter. It adjusts and pushes the power where it's most effective. You don't have to make that decision. You don't have to understand how EM works. You just have to select what you want, in the electronics, and the firmware will do the job to make the most intelligent decisions possible to make sure you get your signal to surface. This makes it very easy to set up and very easy to run. Lastly, we get a battery savings of about 30 to 35%, depending on power settings you set it to, over our previous applied physics EM transmitter. So you can allow longer runs on the same batteries that you used before, or you can reduce your operation cost by reducing the number of batteries on a typical run. And you get the same power output as you had before, and it's more effective because we're transmitting it with the actual power into the formation. So it's all matched. So we're not wasting power. We're not wasting your batteries. We're not creating as much heat as the previous transmitters would. Last thing about our EM transmitter, like I said, it's supposed to be a drop-in replacement. When you use our new G3, not only is it form, fit, and function drop-in for our mechanicals, but it works with all our existing products. Our near-bit short hop technology, it works out of the box. So your applied physics near-bit or dual telemetry or other short hop products all work at that frequency, and the G3 will make it work and transmit this like our old system would. We can transmit our short hop now simultaneously as we transmit to surface, which means there is less of a delay between, say, near bit data coming to surface than it used to be. There used to be like a 20-second delay sometimes to get near bit to surface. Now, with the new G3 technology, we get this simultaneously. So you can get a much more data density and transmission where needed. I think that's my 10 minutes. This is just our standard where our offices are in California, Texas, Canada. Thank you very much for your time this morning, and we appreciate your business and look forward to working with many of you here in 2021.
And Gary, if you want to stick around, for the Q&A session at the end, if folks have some question, in fact, one just popped up. Why don't we address that in the Q&A session, and then we can get the other presenters going then, okay?
Absolutely.
Yes. All right, that's great. Thanks, Gary.
Appreciate
Let's do
your
that.
time.
Yeah. Thank you, Gary. And yeah, we've got a couple of questions come in for you already, so we'll continue to work on those. We're now going to hand over to Joe Doucette, who's going to talk to us about an integrated data approach to landing placement. So Joe, over to you.
Hi, can you all hear me?
Yep.
Excellent. Okay, so let's get this started. And can you? All right, so you seeing my notes or are you seeing the screen?
Seeing the screen, looks good.
Excellent. All right. Hi, everyone. So this is an integrated data approach to landing placement. And the target of this was to land in zones that were less than 2 meters thick. And we're going to go over this pretty quickly, but I think you'll like what you see. So first, we're going to go over why there's little to no data integration taking place right now. Then we're going to talk about how to integrate that data. And I'm going to give you a set of rules for success in doing that. And then I'm going to show you how implementing one data integration method that I call the rule of 84-86 curve landing algorithm, we managed to average 90% plus landing accuracy in a zone that was only 6 feet thick. So first, a little bit about me though. So I'm an actuary that became a directional driller, drilled over 250 directional wells, 112 horizontals. And I've been a data guy most of my life, and I've developed a series of algorithms that really facilitate the drilling and wellbore placement. And as everyone, I think, can agree, the most important thing about any kind of wellbore placement or anything is the curve is nailing the land. I think everybody everywhere can agree that you nail the landing, you're more than halfway there. But let's first look at why things fail. And so what we have here is kind of a current data model. And basically everybody's siloed. There's not a lot of data sharing going on. And if you happen to be the guy in the driver's seat as a directional hand, you're one of the people that gets the least amount of data oftentimes. I've been on several wells where I haven't even been able to talk to the geologists, don't know who they are, or even talk to an engineer or anything. And they kind of keep us pretty much in the dark. But without having that data, oftentimes even our data falls out, and then the entire plan, everything just falls apart. And the end result is the lack of data integration creates this pitfall in our curve landings. People just don't know how to work together. And so let's go over those rules of success. Now, rule number one, I call this just straight up leadership. You got to take responsibility. You can't look at any of these actions and say, hey, I'll just be safe in my silo. So you want to get away from silo safety. We got to move beyond that. Rule number two, data access and data accuracy. The key here is to understand, can you get it and is it accurate? You want to make sure it's stuff that you can use. And then rule number three, and this is one very key point on integration, is remember that one silo's signal is another silo's noise. Or you can turn that around and do it the other way. People, we're all seeing things in our different areas that match up to others. And being able to make those connections is the key to integrating data success. Now, keep this in mind. Yeah, I'm sure you've all heard this. With great power comes great responsibility. No, let's turn that around. With great responsibility comes great power. You need to take responsibility and be a leader at this. All right, so we're going to talk about these perfect curve landings. I'm going to give you an actual example of one. And this method I developed includes the data from all the different silos. And the whole point is to make sure all of that data connects in a usable format that we can use in real time. But the basic idea behind anything in landing a curve is you're going to line it up and then you're going to do a final slide to land it. Straightforward. So let's look at let's apply those data integration rules in this example. And here we have most of it. The only thing missing from this is having a seismic interpretation. But what you can see here, if you can see close enough in here, if you look carefully, you can see you've got what the cuttings look like on the right. You have a whole bunch of gas information on all the different elements that take place as the zones change. And then you move over to the left side, you actually have, on the very left column there, you have actually ROP, weight on bit, actual drilling data in there. And of course, we can see the gamma data. So what you're looking at here is the area where you see on the left there, where the gamma is really high. That's the lower Bakken shale, and that's right above the Three Forks shale, which this example is. Now, I also want to point out another bit of data you may not know about, and I call it directional response. And specifically here, I call it formation directional response. And so if you notice, it says formation directional response, motor yield, minus 25%. Basically, you fall out in that zone. But when you hit the Three Forks, whatever your motor yield was going in, you're going to get 30% or more. So it really comes on when you hit the target zone. So this is our target landing. We want to be able to land inside the Three Forks. So we're going to go through the lower Bakken into the top here. Oh, and one other thing is that there's also a formation directional response that directly affects directional. And it is normally when you cross this interface, you'll get a 1 degree bump in the inclination and a 2 degree break left in the azimuth. So all of these bits of data, you put them all on this paper, it all makes sense, it all looks clean. But the real key is integrating it in real time. So let's start off with the same parameters here. Here's our formation top. So we're going to come in here in the drilling, and who's going to see it first? It's going to be the driller, it's going to be the bit. So we call it drilling response. What are we expecting to see there? Well, it's transition zone, so we're going to see ROP go down, differential go down, and torque go down. Now we move up. Who's following behind it? Well, MWD tools are going to catch up, and we're going to get the gamma and the directional surveys. And what are we going to see there? Well, what we're looking for is obviously the gamma marker, knowing that we have that. Now, drilling's already seen it, so we know this one's going to come up later. So this is the timing. And then we also are watching to see when that survey comes up if we get an extra help, get an extra bump. And then finally, lastly, we've got the gas and cuttings data that are going to come in. And what we're specifically looking for here is that transition where we go from that deep, dark black shale into that harder limestone piece. And of course, there'll be a change in the gas data as well. Now that's the order. That's what you see in real time. And the key is in taking responsibility and integrating is that one leads to the other. So you know, hey, I saw it at drilling, and then it works backwards. And we always look for confirmation. And when everybody works together, it's amazing what you can accomplish, and the accuracy is incredible. So let's look at this real example here. So we've got this target zone, 6 feet thick, it's 11 feet below that top I identified. Gamma's 44 feet behind, and I'm just going to throw this question out here, just to kind of ponder in the meantime. What angle would you need to hit the top of that formation so that you could rotate at least 40 feet, 44 feet to see the gamma marker, and also be able to see the confirmation in the cuttings so that you can land perfectly in that 6-foot window and nail that formation dip? Interesting problem. Let's go through one of these as this solution. So here's what we've got. This is from an actual, this is from my actual tally book of how I wrote this down and put these pieces together. So let's read through it. So I'm currently rotating ahead at 8930 measured depth, and we recorded the drilling break associated with the lower Bakken shale. And so we saw that increase. We go from 65 feet an hour to 120 feet an hour, and we see all the other associated changes. So we're sliding through that lower Bakken. We're approaching that Three Forks top. And based on what we projected the angle at the bit and our anticipated TVD top, made the decision to rotate the last 10 feet that we think is the lower Bakken in order to hit the top of the Three Forks. So call the geologist. Geologist knows we're going to do this. It's all approved. And so we're going to maintain the drilling parameters so that we can identify the negative drilling break. I also happened to place a side bet with the mud logger as to when that would happen. And I predicted 8934, but turns out 8936 is where it slowed down. And it was that dramatic slowdown we were expecting, 110 feet an hour down to 22 feet an hour. Drop in ROP, drop in diff, drop in torque. We continued drilling 5 feet to make sure that we have entered that. And then, of course, we contacted the geologist indicating, hey, the negative drilling break was hit. So now that triggers the next steps. We're going to gather samples, and we're going to be watching as we catch up to it 44 feet later to see if we see the MWD and the gamma markers. And that's what we're looking at there. So we're waiting for that. And then later on, we should be able to see a sample confirmation with both the samples and the gas. And so you put all that together, and what you end up getting is you know exactly from ordered start to finish, based on how you're going to enter, how you need to land. And the accuracy of this method was incredible. We went from hitting it about half the time to hitting it about 90% of the time just by integrating it together. But you have to follow the rules. And that's the key. You got to follow the rules. You got to take ownership, take leadership of this. But when you do and you integrate it together, you can get these great discoveries and have these incredibly accurate wellbore placements. And that's it, folks.
Hey, well, thank you. Appreciate that. And we'll move on to our next presentation. So Michael Kuligowski is going to talk to us about the impact of wellbore placement on the geologist. So Michael, looking forward to hearing about that.
All right, is everybody seeing the presenter slides or the presentation?
We're seeing your slides with the notes.
Okay, let's do that. Okay, does it work now?
Perfect.
Okay, so My name is Michael Legowski. I'm a geologist. I started out my career in the mining industry in metals and coal, and have transitioned over to the oil and gas industry in 2014. And today's presentation will be on the impact of wellbore placement on geology. So I'm planning a vacation this summer, and what we're planning on doing is going from Dallas to Kansas City to visit some family. And then from Kansas City, we're going to be heading west to Denver to spend some time in the Rockies. So to put this in context to a typical well that we drill, let's think of Kansas City as somewhere close to our landing point. If we don't understand where we land and we take the wrong turn, you can end up being on the wrong path very quickly. Both highways are going to be 2 lanes east, 2 lanes west, and they both look the same to you initially. But then suddenly you realize you're on the wrong road and you have to correct and get back on path. And then eventually other actions will happen along the way too, and you end up being in a different road with possibly a different destination. When you get to your destination, both Denver and Colorado Springs look the same if you've never been there before. They have buildings and mountain range to the west. If that's what you were expecting to see, you can be in the wrong spot and not even realize it. So similar things could happen in the subsurface too, where some rocks look the same, others don't. Not all rocks are created equal. So in the example on the left-hand side, we have a stratigraphic column of the Midland Basin from the Upper Spraberry down to the Wolfcamp D. Each one of these will look slightly different in our logs, our core, and sometimes they look very similar to each other. So for example, within the Wolfcamp B, you're going to have different areas of rock that look completely different and may become a little bit more confusing. So if we take a closer look at a section of the lower Wolfcamp B, we have 10 feet of core here. Now, if you've ever seen core from the Wolfcamp section, a lot of it looks the same. It's just black rock. There's some minor differences. But when you start looking at it in further detail, you're going to start seeing some minor differences in it, where you have more shaly rock that could be mechanically weaker to carbonate sections that are going to have a higher mechanical strength. So what I've done is I've taken this section of rock highlighted by the yellow boxes and created this column where we have 24 inches or 2 feet of a representation of sample. And we can see that in the upper couple of inches, we have a slightly different rock. The lower section, we have a slightly different, and in the middle is another. So if we break this up and put in context of, let's say, 8.5 inch bit, we can see that very quickly you can be in one rock versus another. You can be higher, you can be lower, but sometimes in some cases they could look the same, or they can have a distinct signature that could be highly repetitious and can make landing wells and drilling wells a bit of a challenge. So let's take a look at an example of how confusing a landing can be. And as Joe just mentioned in his presentation, landings are critical. If we don't land the well in the right spot, you may not realize you're in the right spot, in the wrong spot, until maybe halfway down the lateral or at TD even. So here we have a 50-foot geologic window of where we want to drill our well, with the magenta line being the target line. Halfway there, we want to land this well in that spot. So here's a blown up example of that particular target window with some traced LWD gamma ray, where the correlation shows maybe we landed in the lower part of the target window, right near that low gamma point. That same pattern can be shifted up a couple feet, and it could show us that maybe we landed a little bit higher in the target window, or it could be even higher. A lot of times, whenever a geologist is attempting to steer a well, some patterns can be very confusing. You'll have the same exact pattern above you, below you, and sometimes adjusting it can be a bit of a challenge. So just purely relying on gamma ray can sometimes lead us into the wrong spots. So for now, let's just assume that we landed the well at the lowest gamma ray marker, which is the first blown up image. So here we have an example of a well that drilled in an area where we can just assume that the structure was completely flat. There was no structure change at all along the wellbore. So we drilled the well, everything seemed okay. And what the geologist will try to do is look at the well data that we have from that well and try to better understand how to plan the upcoming wells. So what a geologist will typically do is look at the ROP. ROP is king, that's what we're told. Drill in the fastest rock, plan the fastest rock, that's what we want to do. That's what's going to lead to our lowest cost. So what we'll do is, where we have high ROPs, we'll say good. Where we have low ROPs, that's bad. And by looking at the rock, we can sort of see that in the first half by landing, we hit the blue spot, which is a low gamma marker, could be a limestone. And we see that in other parts of the lateral too. So we could just assume avoid the limestones, the low gamma, and drill in a shale that leads to better ROPs. So the way this would be planned potentially is avoid the red boxes on the left-hand side. The yellow box shows the section of rock that we drilled, which could potentially be a good spot based on what we've seen. However, in the first half of the lateral, we drilled that section shortly after landing and we didn't see anything unusual. So is there a difference? Why is the ROP different? Well, let's then just go ahead and plan in the upper section of the window just to be safe. We don't know what's up there yet, but maybe it's going to be a less problematic rock. Now, this is just a geologist looking at the data that they have available in their silo. They have ROP, we can understand that. We have the rock, we understand that. But what about drilling? What did they see on the rig? How are they looking at their data? Well, there's some discrepancies between our understanding and theirs. What drilling said is that at the beginning of the lateral, where we landed the well, that low ROP that we saw wasn't attributed to the rock. It was something that they were doing in order to get back to plan. In the middle half, where we saw high ROPs, drilling was saying that that is not a good spot to drill. Yes, we're seeing high ROPs, but what ended up happening was they were having hole stability issues and directional challenges. So while yes, we're seeing high ROPs, they were spending a significant amount of time correcting for it when they had to, or they were doing extra cleanup cycles, which led us to taking much longer to drill this well when you look at it on a days versus depth time. So taking that knowledge that we got from drilling, what if the interpretation was wrong? What if the rock was different than what we thought it was, and we actually drilled higher in section? So let's say that we drilled now in the high gamma marker that's closer to the top half of the target window. And these are usually these hot shales that we typically refer to them in the Permian. And these shales will usually kind of suck you in. You'll get great ROPs, but you will have hole stability and directional issues with it. So in many cases, we don't want to drill those wells just because we have these challenges, but then also completions can end up having problems initiating their fracs in there. So by looking at this data from drilling in geology, we can realize that the plan that we had to drill in the upper part of the target window is no longer valid. We want to make sure that we agree with what drilling's notes are saying and go ahead and change our plans to drill in the rock that's going to give us not only potentially better ROPs, but less drilling challenges that lead us to having trip outs or unnecessary failures, which will then lead us to a more successful well, not just purely based on ROP, but avoiding general drilling challenges, which will eventually slow us down. So in conclusion, the wellbore placement is very important, because if you don't know where you're at initially, how will you know where to plan your future wells? If you drill in a spot that's problematic, but you don't understand where it's at, you may very well end up in that same spot. So the success to all of this is proper communication between the different silos. Drilling and geology must talk to each other. Geology must use all the data that's made available to them from drilling and vice versa. So that way we understand each other's data. So that way when drilling is indicating something, geology can use that information to understand that maybe we aren't in the spot that we thought we were at. And that is it. Thank you.
Thank you, Michael. And now I think we have one scheduled presentation left, which is David Gutierrez with Superior QC. He's going to talk about the impact of wellbore placement on reservoir and on the field development. So, and yeah, there we go. We can see your slides.
Important topics. I am David Gutierrez. I work for Superior QC. I'm a technical advisor over here. And our primary focus is wellbore placement survey management. And today I'm going to talk a little bit on the impact of wellbore placement on the reservoir and field development. So let me get started here real quick. So what I want to start is where are we at as an industry, and what have we primarily been focusing on and putting our emphasis toward in regards to wellbore position, and then where do we need to go? What do we need to shift our focus toward in the future? So I would say that we've done a really good job over the last few years of really beating it over everyone's head in the industry that MWD surveys, magnetic surveying, is not without issues. They do suffer from some errors, especially the magnetometers, as has been previously touched on in this presentation. The importance of that on well-to-well spacing is paramount to ensuring that we're going to be doing the most for our operators in completing these wells and getting the most out of these from a production perspective that we can. So I would say this is something that we're doing well right now. Most current operators are aware of this issue and are at least taking steps toward mitigating some of it, if not running outright survey management on all of their wells. So I would say this is what we're doing well. So what is left now? What can we really shift our focus toward in order to continue our growth in wellbore position accuracy? And I would say what's left for us to do here is implementing real-time corrections in the TVD plane. I think our fellow presenters here, especially Joe and Michael, have been touching on the TVD plane. Like, there hasn't been a huge improvement in what we're doing from a TVD-wise perspective. And I know that Nate previously mentioned Ed Stockhausen and his idea of capturing the shape better between those 95-foot course length surveys. We know now as an industry that minimum curvature can inaccurately place the TVD of the shape of that wellbore over that 95-foot course length. So I think this is some of the stuff that we still have that we can improve on as an industry. So let me take you through some of the options as we see it in Superior QC. This is primarily what we've been putting a lot of our focus on over the last year or so, is trying to come up with a better answer for what we do in the TVD plane. So to start off with, BHA SAG corrections, I'm not speaking to anything here that everyone on this meeting isn't aware of. So essentially BHA SAG is that we're trying to get this MWD sensor in alignment with the actual wellbore, and the placement of that sensor can be an error just due to sag of the non-mag drill collars that the MWD tool is sitting inside of. So we have a good framework around this currently, and we want to make sure that we implement this so that we're not inducing error to the positioning of the wellbore. So the next things that we really want to get done here are how do we actually take Ed Stockhausen's principles and how do we put those into effect going forward in a real-time fashion, and how can we use this to partner with geology, as Michael previously mentioned, to give them more information to land the well properly, like Joe mentioned. So how do we take these principles and apply them to drill this well more accurately? So what I'm going to do here and show you is how we have approached that problem. And I'll do it through an exercise of a couple of case studies that we've partnered with operators on. So this was a well that an operator brought to us post well. We did not provide corrections on this in real time. they were using survey corrections real time, but they weren't primarily focused on the TVD, right? So not many correction providers out there have a good answer for TVD. So this is a geological interpretation of the landing zone. So how can the Stockhausen effect negatively impact the landing of the curve? In black here, you see that the well, when drilled with traditional 95-foot course lengths and almost no additional information in between, they actually land a little bit deeper. The window is shifted down. But when we used high fidelity navigation, which is what our product name is for taking into account Stockhausen effect and some of the additional information that goes on between surveys, what we identified here was that the well was actually landed approximately about 8 feet shallower than was originally interpreted by traditional surveying. So the question is, how does this occur, and how do we get this information to the operator more quickly to make decisions in real time? So the additional information that you're going to require as you're drilling this well is the steering and non-steering, sliding and rotating intervals, and the tool faces which they held over those slide intervals. So this here is a measured depth plot versus inclination, and primarily zoomed in on the curve section. What I want to highlight is the difference between this blue line, which is just your standard 95-foot course length surveys, and then the black and red is when you take into account your sliding and rotating intervals. So what was happening on this particular well was a survey would be taken, and when they went to go make their slides to build up that inclination to land this curve, when they started mixing in rotation is where this landing point starts to grow an error in TVD. So what you can see here is when you're sliding, that's where you primarily expect to see your angle change. When you're rotating, you expect it to be relatively flat. Not perfectly flat. You're going to have tendencies that will attribute to some behavior in between there as well. But if you're sliding and rotating over those course lengths, especially in the manner in which they did on this particular well, sliding right after a survey and rotating toward the end, what you can see is you're actually achieving that inclination earlier. You're spending a lot of time above the MWD survey inclination line in blue here. And what that does is that manifests itself into TVD error that is shallowing your landing point. And that's exactly what we saw in this well. And when we provided this to the geologist, confirmed that this information was a little bit more accurate. You can see that you get a little bit flatter response from your geological interpretation there toward landing. So what about after landing point? We talked about getting it right from the perspective of landing that curve, but what's going on for the rest of the lateral is also important. What we saw in this particular well was a misapplication of sag corrections. So they were running sag corrections. What it looked like was that we were observing, when we did our analysis, that the sag calculation was correct in magnitude. However, it was applied in the opposite direction. And just by taking a look at the left-hand side of the screen here, we're highlighting how we came up with our sag application. So you can see, just based on the schematic down here on the bottom left, representing their BHA and contact points of stabilizers, they're essentially past this inflection point where the sag correction, if you look at it intuitively, should be positive. In order to bring that MWD sensor back to the center line, you're going to need to apply a positive correction, which is what we found out when we were doing an analysis on this well. So if you essentially take this 0.13 correction, flip it, and apply a negative 0.13 for each survey, what that does is it accrues to nearly 50 feet of TVD error throughout the lateral of this well. And I think more importantly here is that you can see that it affects the dip angle, the formation dip that's interpreted by the geologist over the course of this lateral. So they know they landed high. They know that they weren't where they wanted to be. So what they did was slide down to try and get back into the target window here. But with a misapplication of SAG here, what you can see is the surveys taken in real time, represented by the black line, was showing that they were coming down quicker than they actually were. When you do a correction for the SAG using a positive SAG calculation, at best they're coming down a little bit, and for the most part, really just staying parallel to the top of that window, which eventually requires this big drop about 2/3 through the lateral to try and get back in that target window. So you can see here how TVD corrections can negatively impact your ability to stay in the target window, which ultimately could cost you a lot of money if you're not staying inside the target zone. So here is a gun barrel plot of all the wells on that pad. So it was a 3-well pad, and it's represented by well 3 over here. So let's just look at what the geologist was seeing over the first couple of wells here and how it had impacted well 3. So, oops, sorry about that. The darker color is representing landing point, and the lighter shade of that color is representing the well at TD. This is taking a look at Hi-Fi Nav's solution in red and the non-Hi-Fi Nav solution in gray here. So what we see on wells 1 and 2 is that we have a down dip that we're kind of following throughout the lateral, coming down a little bit in TVD throughout. And on well 3, that's what the geologist thought he was getting to. But as I highlighted on that previous slide, due to a misapplication of SAG in the lateral, what was actually occurring was that mostly we were staying parallel to the top of that window, and we weren't actually getting a good interpretation, and that was due to a misapplication of TVD corrections. So what we really missed out on this particular well was the TVD corrections actually cost us a missed landing point zone, and that was due to the Stockhausen effect. And additionally, throughout the lateral, we misidentified the formation dip due to BHA SAG correction. So ultimately, we could have, if we were applying real-time TVD corrections here, made a bigger effect on the TVD of this well and had it been more accurate from the real-time perspective versus doing this post-well. So here is one additional case study before I wrap it up, which has a very similar outline. This was a 3-well pad that a geologist brought to us, and they did so because if you can see here on this topographical map, the 2 outside wells agreed quite well from a TVD perspective, but the middle well did not line up with the other 2. They were supposed to have been drilled in the same formation, the same TVD, and what happened was the geologist wasn't getting a good correlation with those 2 outside wells, but his gamma was matching up really well, so he was trusting his gamma, drilled using that, and it ended up being that middle well looked like it was 30 feet shallower. So in order to compensate for that, there has to be some sort of assumption that there was a double fault valley or something between these 2 wells, which didn't make a lot of geological sense. So when this information was brought to us, we processed it with our base calculation or survey correction algorithm, which is FITR, which is the most comparable thing that we have to multi-station analysis, which does not account for these TVD corrections, and we came up with a very similar result. But when we processed this through Hi-Fi Nav, taking into account Stockhausen effect, SAG, and that TVD correction, what we identified was that middle well was actually 30 feet shallower than the TVD of these 95-foot course length surveys alone. So from a pad drilling perspective, and I guess this will be the question I leave with the group, is how can something like this impact reservoir modeling infill drilling? So how can having an incorrect TVD and an incorrect topographical map of your area impact your reservoir modeling and negatively impact your plans for infill drilling, especially if you've got staggered zones, and if you're in thin zones, what can this do from a planning perspective on field development? Thank you.
Hey, thank you, David, for that. And that takes us, I guess, into the questions, and there is actually a question coming from John DeWart that really ties in very well to the end of the your presentation there. So I'll put it out to the whole group. Everybody that's presented today, feel free to pitch in, but maybe we can start with you, David. And John's question was, how well do subsurface people like geology, reservoir engineering understand what the certain uncertainty is in the position data that they use? And I think in John's question, I don't know if you can read it, but John's contrasting the fact that we give multiple decimal places in our survey data, which gives this kind of illusion of accuracy, with the fact that there is actually uncertainty. And do the people that are using it actually understand that this is that we know there are errors in the data?
Yeah, that's a great question, a good one to start on. I think kind of touched on a little bit in the morning session of this same group, but it goes back to what is the communication level between the different groups. A lot of the times when drilling is executing the well, the geology department is not aware of the fact that there is even such thing as an ellipse of uncertainty, and especially how that can impact the positioning of the wellbore. I think some cross-pollination between the business units would really clarify a lot of what we're trying to manage from a accuracy and what we're positioning point of view. And I think that there's a lot to be left on the table for us to do as an industry, because like you said, you're providing accuracy to 2 decimal places, but your ellipse of uncertainty can be 250 feet half width left, right. So what does that really get you in level of accuracy? I think it's a great question.
Anybody else on the panel want to pick up on that or to add to that?
Yeah, I'd like to, very well spoken there, David, on the different pieces. I mean, one of the integration events that I found that helped tremendously with this, for example, is what I refer to as formation directional response. And I liked how in your slide that you showed that when you slide first, for example, and then rotate, or rotate first, then slide, you know, if you are taking 95-foot surveys and miss that event, your TVD is going to be way off, that's for sure. But in the horizontals, it gets, what I've also seen is documenting that you cross certain markers and you get a lot of help. And so you'll have these micro small dog legs. And what I've tried to do, and usually you get shut down for doing this, is to help the interpretation just survey so you catch that little micro event. And so that way, when you get back in, otherwise I've had too many instances of all these false dips where, you know, the whole formation's going up, but just because of the timing of the surveys as we're going through an undulation, you know, the whole thing shifts. I like the way you've accounted for, or how you've accounted for that in your.
Okay.
One thing I'd like to add to that, since Joe seems to have been cut off, is while we do know that there's, from a geology perspective, one of the challenges we have is trying to accurately model the subsurface. We have a lot of our data based on historical vertical data that doesn't have proper surveys. So we treat those wells as a pure vertical. So that's going to give us a artificial thickness and depth that's not realistic. But the key is not to think about the rock and the subsurface as TVD subsea or TVD depths. We need to look at it on a pure rock basis. So when we're transitioning to these different markers, we know to a certain extent what the thickness of it may be or where it might be relative to a nearby log. So instead of trying to create these surfaces as a big real depth model, we should be focusing on them as a sense of what is it on a stratigraphic depth basis. So from a certain, you know, data marker, create these models to focus just on the depth of the rock, not structure of the rock, but what the thickness of the rock is. So that way, when we are executing these wells, we know to a certain extent what's above us, what's below us, what's in front of us, without worrying too much about the structure and the depths itself. So it's a multiple approach to trying to figure that out and take that equation of that component of depth error out of it.
Okay, so any of the presenters from the first half want to comment? Adrian, Ross, Nate?
So I'll turn my camera back on. Yeah, I do. I think we have a bit of an uphill battle here. I think with we've been talking. It's not like subsurface people are unused to uncertainty, but we have a bit of an uphill battle in getting them to understand the uncertainty associated with drilling. And I think there's been some moves, and I think there's some moves afoot within the SP to try and bring those two things together and come up with a combined, almost a combined error model that brings subsurface uncertainty and drilling uncertainty together to give people a much better idea of what they're actually dealing with. Because some of the numbers are quite petrifying, large. I mean, you know, we routinely get asked for you know, I want a 1 foot TVD window to drill through. Well, fine, when you find that 1 foot TVD window, we can stay inside it, but trying to find it in the first place is very, very difficult. The real disconnect about what is actually possible from a professional drilling point of view.
Okay. Any of you other guys want to comment? It's very hard. You can't get eye contact when you're in a meeting like this, so it's really hard to know if somebody wants to speak up or not. But
I think it was covered, but yeah.
Okay. So I've got questions coming in on YouTube as well as questions coming in Zoom. So if we take one of the questions out of YouTube from Oscar Sanchez, says, some operators have gone to plan the first well on the pad for the deepest target TVD, so that for the remainder they could have a gamma ray sweep of the entire of the target. And he also says, based on this, staying in the sweet spot within the window is critical, not only for wellbore deliverability, but also for ROP optimization, vibration mitigation. Does anybody want to make any comments on Oscar's? I guess it's half a point and half a question there.
Yes, that is a good approach. Some operators I know will attempt to do that, land the well low, get a good type log to use for correlating, and then you have some understanding of the rock. So that will work in some areas. In some parts of the Midland Basin, we would drill a pilot well and have it cored. And when you build the curve off of it, you'll see markers disappear on you. And it's the most odd thing where you can't correlate back to it. But in an ideal situation where you have continuity, that is a good approach to have.
Okay. Anybody else want to comment on that? Okay, and then there's a question from Mark Willeth. This is to one of our presenters. On your plots, you show a reduction in TVD uncertainty due to corrections, and curious as to the justification for that, given that the Stockhausen effect is considered outside of the error model.
Well, that's probably targeted at me.
I think so, yeah.
Great question, Mark. Thank you for your question. So you're right. We did show a reduction in the TVD uncertainty due to the high-fi nav corrections. There are a couple of error terms that we're targeting with that. They primarily focusing on the misalignment with respect to the wellbore terms and a little bit of additional reduction in the SAG uncertainty. I'm sure these are things that we'll talk about in the ISC-WSA subcommittees, but those are primarily the terms that we are targeting with that.
Okay, and then there's a question from Canute about the how to calculate the Stockhausen effect on motor versus RSS. And I'd always thought of the Stockhausen effect as being something that you illustrate by looking at with motors, you know, sort of slide rotate intervals and stuff like that. Anybody want to comment on the question about how you calculate it for motor VRSS?
Sure, I can weigh in. So what I would say is you would expect a smoother wellbore for the rotary steerable, and I in general would not disagree with that. However, there are sections over a course length where corrections by a rotary steerable are occurring, so basically steering events and non-steering events. So you can still represent the Stockhausen effect. It is a little bit more complicated. The steering does occur more often, and the deviations are typically smaller. However, there are still some sections where steering and non-steering do occur. So there's a little bit that can be modeled there, but I would agree that it's generally on a much reduced scale.
But that's going to depend on the way the rotary steerable is set up and how long those steering versus none, and whether it has proportional steering or not, and if not, how long those steering versus non-steering sections are, what the period is, I guess.
Can I just add to that, John?
Yeah.
With a rotary steerable tool, especially with a high dogleg rotary steerable tool, you really can create very large TVD errors very fast. And the problem is that the geologist is constantly asking to nudge up, but that nudge up is never seen by the static survey. So it's very like the Stockhausen effect. You're continually going up and up and up, but you're not seeing that change in TVD, and it can have quite a big impact very quickly. But often it's much more random than the Stockhausen effect. So you're both nudging up and nudging down. So the effects kind of at the end of the well, it might look like a big change in TVD, but over a short section, it can be quite dramatic.
It can be, okay. Okay. And I think we've got time for a couple more questions, yeah?
John, can I weigh in on that one too? Yeah,
one of
the most interesting things that I've encountered with rotary steerable that directly relates to this is oftentimes you'll see yourself skipping off of something. And sometimes it'll show up in the gamma, sometimes it won't. And so in those respects, I imagine continuous inclination could help a lot, at least to identify if there are certain zones that you cut that have those little minor, major, sometimes you see this 6-degree break in azimuth with a 1.5 degree surprise. And I think if you don't accurately survey around those, yeah, you'll get off really, really, really fast.
Okay. And I think Gregory Devenish just made the point. It's not really a question, but he's added into the conversation that the TVD uncertainty will be greater if the rotary steerable uses a duty cycle rather than continuous because of rugosity. So that kind of makes sense. I got a question from Robert Wiley. And Robert says that Joe did a great presentation on use of all the real-time data to land at the desired TVD. But what does the panel think about DDs getting ahead of the curve and landing long, and the impact on the well economics and the impact on geologists' understanding of exactly where they are? So who wants to answer the question? Who wants to take the question first about landing long?
Landing long is evil. Okay. A lot of when you're drilling, I remember first drilling in the Barnett Shale, and you have these really, really short laterals, and to see guys get way ahead on the curve and go for soft landings or other things like that, it just eats up vertical section to know, all the way. So, I mean, the purpose of that, what I put together was also to maximize that vertical section and minimize the amount of curvature. So you didn't end up, throwing huge dog legs right at the end, or, get so far ahead that you're rotating forever and having to eat up vertical section. So to me, on the economics, the win-win, the real thing is, for a directional hand, yeah, the casing better go down, but at the same time, considering the cost of every foot that you lose in vertical section, that's something that you must account for.
Okay, so we've heard it's evil. Anybody else got any comments? I'm going to remember that. I'll use that.
In
no
terms
other comments?
Of geology,
here we go.
If we build ahead, we still will understand where we are. I mean, we know what the angle is. we have the gamma ray, we know exactly where we are. So it's not going to have an impact on geology. It will have an impact on the economics because you're just losing section of the well that you were going to have. But in some cases, we can't control that because there are spots, for example, in the Eagle Ford, that you're going to be unable to build that curve. So sometimes getting ahead of it is required. And if you get the thicknesses wrong on those, people call them dead zones, it will impact on it. So it's just part of a communication between drilling and geology to understand where we may have spots where it's going to cause us challenges with building the curve.
Okay. Anybody else want to comment? And if not, I'm going to hand you back to Jim, our host, because we're slightly past our finish time, and we're actually getting close to my next commitment. So I'm going to say thanks everybody for the great presentations, for the good dialogue during the Q&A. Thanks to the audience for a lot of interesting questions. I think we managed to get through most of them. And thanks to Jim and IEDD for hosting this. I'll just pass back to Jim to wrap up.
All right, John, thanks for chairing this session. It was a good job. There's a couple of things. Since we have rescheduled session 2, probably be early next week. We'll get that announcement out. We can go ahead and finish these up, or if there's any wrap-up comments. Brian Dugas has said the RSS will apply the maximum program build steer force to get the desired inclination, then maintain that inclination to the next downlink. So I guess that's a comment that tying into the motor versus rotary steerable Stockhausen effect. We have a question, David G. Can you elaborate a little on how the sag misapplication was identified and how was it separated from other potential error sources, i.e. the Stockhausen effect?
Yeah, sure. So like I kind of tried to explain on my slide, BJ sag is really just a geometry problem. And especially knowing the inclination angle, you can know essentially, and the BHA makeup and the sensor location, you can identify which direction, first of all, you should be applying sag and the magnitude. So that one you can really break apart on its own without really doing any deep dive analysis into like the 6-axis data or anything like that. You're really just taking an inclination and applying it to a geometry of the BHA. The Stockhausen effect is going to be mainly contributed on understanding where your slides start and end depth and your average tool face held over that slide interval, how that impacted your wellbore. So you need to know where you're sliding and where you're not sliding. And that is information that we take into our Hi-Fi Nav solution. And we also take in, I think like Nate mentioned a little bit earlier, the continuous inclination and azimuth in order to verify, validate, confirm our model's estimate of what's going on in between the survey stations. So they're kind of two separate problems. And then we give a combined solution in real time.
Yeah. Yeah, Robert Wiley's going back to the rotary steerable ones, made a comment that depends very much on which rotary steerable system is being used and at which mode. Real-time feedback from the RSS on what is doing is invaluable to understand the whole shape in real time for good decision making. I think that's a carry on to some of the other comments here. Does anybody have any comments on that they'd like to put into place? I think you got them, Robert. All right, Gary, if Greg Devenish made another comment, and the talent of the directional driller, that does come into play. That does come into play. There certainly is a lot of Gary, if you're still there, there was a question from Juan Penaranda about the tool. Let's see if you can unmute. He may have had to slide off. The question was, does the tool have any has any ROP limitations?
Not as far as we can tell. Our EM tools have been used 20 some years, and we're not changing the fundamental mechanics or design when we're changing the transmitter. So it will have the same ROP limitations that our previous EM tools. You have some build rates you can accomplish or not accomplish. But other than that, no, there are no ROP limitations to this transmitter.
Okay, good. Do we have any other comments from the panel? Here, any final wrap-ups? Okay, well, with that, I want to thank everybody. Gary, thanks to Applied Physics for your sponsorship today and for the information, and to all the panelists for their participation. As I mentioned earlier, we will start again tomorrow at 10 o'clock, and we will have sessions 3 and 4. I've been texting back and forth with Ed during this session, and it looks like we'll try to get that session 2 rescheduled for next Tuesday. We'll get the information out and confirm that. So with that, thanks again. Everybody have a great day, and I hope to see you back tomorrow.
Glad to be part of this.
Everybody take care. Bye-bye.